Thank you very much. My name is Rudolf, or just Rudy. I'm located in Vienna, and I've been working roughly 15 years around data analytics, mainly with Microsoft technologies. And I also run my own consulting company called Home Data. Think before you code reflects a simple idea. In our data bubble, we focus in our discussions heavily on new tools and the latest features and so on. But quite often, I feel we're skipping the most important step, and that is actually thinking first. During the past years in my career, I have spent hundreds of hours writing SQL statements, debugging ETL pipelines, and overall trying to understand why solutions behave the way they do. Sometimes problems have not been easy to fix, and I realized at some point it's not always the engine or the SQL part, it's very often missing concepts. And this is the reason why I want to talk about stopping habits in our projects that make our lives harder and instead adopting habits that make it easier. Throughout the session, we will follow somewhat the same path I went through myself, from the general to the specific. First, we'll step back and talk about a few core concepts in data and analytics, independent of technologies. Then we zoom in on the technical side and talk about SQL and the engines processing SQL. And after that, we will move on to understanding meaning of data. Finally, I would like to wrap up with a couple of small practical habits that you can apply immediately if you want. And let me say, this session is not about fancy code. It's about thinking things through before we even write a single line of it. So let's start with some concepts. The main concepts behind data and analytics systems date back to the 1970s, and yet decades of collected knowledge and academic research seem often not to be taken into account in the everyday projects. And I would say they are not for architects, they are practical tools we should apply in our work. So if you miss the concepts, you will still build solutions, but your solutions may return wrong results, they may perform badly, they may be hard to maintain in everyday operation, or they even break when the data volume rises or requirements change. A data solution we are building in a data project naturally sits between the sources that produce the data and some clean business expectations with pretty reports the deciders in business want to have from us. This fancy black box in the middle we are building has to support a lot of functions. It has to connect to different data sources with different technologies. It has to align mismatching data, coping with different business processes, meanings, and also ambiguities, calculating complex KPIs, dealing with bad data quality, and also dealing with changing requirements over time. And all of that, I would say, leads to one thing, and that is complexity. And we have to manage this complexity in our projects. If we don't do that, it will come back as technical debt and pain like performance problems, wrong numbers, and so on. I would say there are three main drivers for complexity in a project. First of all, that's a business. It's the overall context where our data that we're working in comes from, and also where the data or the reports that we produced are consumed. It's about the terminology, the industry knowledge, and so on. Second, there is the tools and the technology. Most of the time at the beginning of a project, we decide for a certain tool stack, and then we have to work and to live with its strengths and its weaknesses. And third, it's us. It's the people that work in the projects, and I would even say more specifically, it's the way we work and we work together. That's, for example, the project organization, the collaboration between teams, but also within a team, and the overall consistency that we deliver our work. And I would say we have, as an individual in a project, very little influence on the two pillars, business and technology. But what we can change for ourselves is how we think and how we work. And so with that, let's dive into a few core concepts. One fundamental concept, I would say, is the difference between transactional and analytical processing. On the left-hand side of the slide, you see a catch register print, and the system that produces this print is a typical example for transactional processing. It's optimized for a fast, small change of individual rows, and its goal is a very high throughput of small scoped transactions in a short time period. On the other side, on the right-hand side, you see some drafts for business reports that try to deliver aggregations over the whole company about sales, for example, and this is a typical analytical processing use case. Here we have to scan over large amounts of data within one transaction. We apply aggregation logic in the calculations. Our queries scan whole tables, and the overall goal is to quickly query a vast amount of data. And so when we treat an analytical use case like a transactional one, we will end up in performance problems. So the first thing is always to think, which use case am I working in? The next concept is time and tracking changes over time. When it's about time, the easiest, I would say, is real life. We are here in the now. I'm holding this presentation. There are some memories about yesterday and who knows what will be tomorrow. But when we start to analyze and track changes over time in data, and we start maintaining versions of what we knew at a certain point in time, things get interesting. And let us have a look at a small example. What you see here is an example CRM system that may have a row about me as a customer, and it was entered at day 1, and there were some updates on a day 2 and a day 3. And let's have a look how a transactional system as the CRM and a data warehouse would treat this information. On day 1, the newly created row is both inserted into the CRM system and in the analytical system in the data warehouse. Yet, in the data warehouse, we add a time information when we got to know about this insert or about this data, and this information we will need later on for versioning. On day 2, the CRM system simply updates the row with the new information. But in data warehousing, we do not update. We want to track the changes, so we add a new row and again add the version date to it. So at this point in time, we already have multiple versions of one business entity in our table. Day 3, same thing happens again. We're adding the new version in the data warehouse. And when we look at the data warehouse table now, the crucial takeaway is the versioning changes the way we have to write queries. Because when you query historized data, every query asks you an implicit question, and this question is, which point in time do you mean? And you have to answer this question explicitly if you want to produce reliable and reproducible results. And if that's not enough, we can take it to the next level, and this is several timelines. There are some source systems that allow users to backdate changes in a way that when you do an update or a change on the data, there is a separate time or date column where the business user can state by which point in time they want to treat the update as effective from a business perspective. And this is then a new date column. We added it here as a valid from date in the same example as before. This introduces a second timeline to the one that we already have from the technical historization in the previous slides. And now let's have a look again into the systems. On the first day, it's fairly similar. The only thing is we have this new valid column. I called it valid from date here in the source system. And we add it again to the data warehouse, But in the data warehouse, we already had the technical version date. So now we have two different timelines in the data warehouse. The technical one that tells us when we learned about the change, and the business one, that's when the business user said it became valid from their point of view, whatever that means. And this is called a bitemporal history. On day 2, the same pattern as we know, we just add the new rows. Day 3, again, we add the new rows. And now let's have a look again at the data warehouse table. When querying, remember from the previous slides, we said there is the implicit question, by which point in time do you mean? Now suddenly, wait, we have two timelines. So which one am I picking? The technical one or the business one? Or should I combine them in a certain logic or a way? And every answer you can do to this question will lead to a different query result. And this is the important thing to understand. So overall, this example is intentionally simplified and it will probably not occur in real life as you see it here. But my intent is for you to recognize the trap that complexity grows faster than you expect, especially when you're working around time and historization. So always think about the time-based aspects of your data when you're working with it and explicitly decide how you want to handle them. If you don't do that, I'll promise you sooner or later you will end up with inconsistent results. And there is another flavor how time-related data can occur, and this is events or transactions. And these are easier to understand, I would say, because events are by their nature atomic. They happen once, and then they usually don't change. So the processing is fairly simple. We capture when they happen, we capture their attributes, and we just insert them, both in the CRM system and in the data warehouse. Yet, as always in the data warehouse, for audit reasons, we capture the date or the time when we got to know about them. So now, as we've sorted out the trouble around time, let's move on to architecture and data modeling. The two terms, data architecture and data modeling, I would say are closely related, but they are not the same. An architecture describes how a data platform is structured. So how the data flows through its components, and it's typically organized in layers or zones. And it also covers technology decisions and processing patterns and things like governance. On the other hand, a data modeling approach describes how the data itself is structured. It is most of the time applied within a layer of an architecture and describes the logical shape of the data and also how the business concepts are represented in the tables. And there we are working with keys, relationships, and so on. So in summary, the architecture describes the system layout, and the data model describes how the meaning is encoded. Over the next slides, let's have a very brief look on different architecture or architecture blueprints that are very common. First, there is the data warehouse as described by Ralph Kimball. It is in the focus, very business process driven, and it focuses on reporting requirements. And it also introduced the concept of dimensional modeling and star schemas. By that, it focuses heavily on the data consumption and the reporting part, and also almost all the BI tools that were developed in the past decades, I would say, are heavily optimized for working with star schema models. And I would say this is also the case for Power BI. As a next one, there is the enterprise data warehouse described by Bill Inman. Its focus is, as opposed to the Kimball style, more on an enterprise-wide data integration before thinking about how to present the data in reports. So to achieve this, it introduces a new layer. It's very often called core data warehouse that should act as a single point of truth for all the subsequent layers or reports. This core layer feeds the star schemas, and by that it tries to avoid siloed reporting. And also in this core layers, very normalized data model is suggested. Next, there is Data Vault. Data Vault, I would say, is some sort of an advancement of the Inmon enterprise data warehouse ideas with more focus on decoupling raw data historization and storage from business logic and business calculations. It works with highly standardized loading patterns to allow a high grade of automation. And the overall goal is scalability and changeability of the overall system. So adapting to changing business requirements ideally should be facilitated through additive developments and should not require refactoring. Ideally, not at all, but it's not always the case. And last not least, there is the medallion architecture. We also heard a lot in the previous session from Benito. So to talk about medallion here is almost obsolete. Watch his session. But what I would take away here, for me personally, the medallion architecture as it is described is, strictly speaking, for me, not really an architecture similar to the previous ones. It's more concept describing data layers by data quality stages. So it suggests to organize your tables by the level of data cleansing and logic and so on you have applied. So it remains, as opposed to the previous ones, very vague by design, I would say. It, for example, does not specify dedicated data modeling styles for the silver layer. And I've heard different opinions out there whether you should apply proper or sophisticated data modeling or not in a silver layer. There are different opinions out there. But what they all have the same. So what I would like to stress here first, there are plenty of blueprints out there. These were just a few very common ones. And what they all have in common and what we see very nice when comparing to this medallion architecture, they all organize the steps in layers with different functionality, and they represent different approaches for the same goal, and that is making analytical data usable for business. And with that, I would also encourage you, don't see those architectures or methodologies as religions. They're tools, and they are addressing problems in a certain way. And I would like to encourage you, read about them, read the ideas behind, because that will help you understanding the patterns and the architecture decisions in your own project. Even if you're not an architect and if you're not doing the decisions for yourself, understanding why the things are designed in this way makes the daily work way easier, especially when things go wrong and you have to sort out problems. So up to now, we talked about concepts, and now we would come to the fun part. We write code. No, not yet. Wait, I have still something to think before we start coding, and it's understanding how the engine works under the hood. And for that, let me start with a little story. When I was a kid, I was really fascinated by some genius on a very popular TV show back then who could save the world with just a paperclip and a piece of chewing gum. I guess you know who I mean. And so one day I went to the hairdresser with a photo I cut out of the TV newspaper and said to the hairdresser, "I want to look like this. Please make it possible." And nowadays, I'm writing SQL queries that may look like this one you're seeing here. And I say to you, in both situations, I did the same thing. And I would like to ask you, do you have an idea what did I do in both situations? Write it to the chat. What is your first idea? I will give you a few seconds. Thank you, David. SQL is always sexy. Okay. I'll let you know. I was describing the result. So at the hairdresser, I was not explaining something about how to take the scissors, work with which angle, or the steps to do a certain hairstyle. I didn't have an idea about that, and I still don't do. But I described what I want the result to look like. And writing SQL is the same thing. SQL works the same way. It is declarative, and this means you're describing what the result should look like when that you want to be produced, and you are not describing the steps to execute to produce it. So when we look at how SQL Server processes a query, it takes two things. The first is the SQL statement you wrote, and the second is everything it gathered that it knows about the data. These are the data structures themselves, the relationships between the tables, constraints, unique keys, and foremost data distribution, statistics, and so on. And the query optimizer then generates multiple alternative plans that would lead to the same result. And it estimates the effort it would have to execute these respective plans. And then it chooses the one it thinks is the cheapest for the actual execution and passes it on to the execution engine. So the important point to understand here is when you write SQL, you're not directly giving commands what exactly to execute. You're describing a result, but still the way you write your SQL influences the optimizer's choices and capabilities. And this is important to keep in mind. And one of those influences is processing logic. Relational data in general, I would say, can be processed in two modes. It's in a row-based logic and in a set-based logic. As the naming suggests, row-by-row logic operates on a single data row at a time. It takes one row, does its transformations and calculations, and then moves on to the next row. While a set-based logic operates on multiple rows at a time. So these are operations that scan over whole tables or sections of tables, apply aggregations, apply windowed functions, leverage union operators, and so on, for example. And SQL in its pure form, as it's described in the ANSYS standard, is actually declarative in its nature and encourages by that set-based thinking. Yet, the vendor-specific implementations like T-SQL or PL/SQL introduced procedural extensions that contain imperative constructs and allow source control flow structures. And that makes row-by-row processing possible. And when we don't think in sets, also very tempting. And for you, I would say it's important database engines can work in both modes. And in transactional workloads, also row-by-row processing can be fine when you don't hit certain amounts of data and data throughput. But in analytical workloads, treating data row by row almost all the time breaks scalability at a certain threshold. So if you want to ensure analytical scalability, this almost always means you have to think and to work in data sets. Another very common trap is applying object-oriented thinking to SQL. What you're seeing here is the slightly tidied up dependency tree of a real SQL store procedure I had to reverse engineer once. And it contained cursor logic directly in the store procedure and then called chains of nested views that called another view, another view, another view, another view. And if you've learned object orientation with languages like Java, .NET, and so on, this feels very clean, but it hides away what really happens at execution time. And in SQL, as SQL ticks a bit different, this abstraction can easily turn into opacity, and opacity kills performance. So my experience with SQL Server, for example, is that at a certain level of abstraction, the optimizer fails to produce good execution plans. Unfortunately, as always, there is no rule of thumb. But my experience is, or how I'm working, if you stack more than, let's say, 3, maximum 4 layers of views in one logic after another, I would start to be cautious and really have a look at performance. So try to think in data sets and structure your solution around that. Of course, you can use views and are encouraged to use views, but I would like to encourage you not to encapsulate every single transformation step in a separate abstraction layer, but think more in sets and, for example, in intermediate results and put those in an abstraction layer. Well, the next chapter brings us to the data itself. Because you can have smoothly running SQL, you can have applied everything we've talked about before, and your results can still be wrong when you don't understand the data you're querying. So from this point on, let's shift our focus from the engines to the meaning. And understanding data means understanding its semantic meaning, and you can have a look at it in 2 directions. The first direction is you can have a look at it upstream. With that, I mean towards the data sources and asking yourself the question, who produces this data? Where does it come from? Is it entered by a human or is it produced by a machine? When is it updated? What is the business process that produces the data? And what parts of the real world does the data actually describe? And the other direction is downstream towards the data consumption. There you can ask questions like, who needs those results? What are their business questions they want to ask? Or which decisions do they want to make with the data? Why did they want to have the report look like they said? What happens with the results? When do they need them? And there, I would say the most effective optimization technique, surprise, is talking to your business stakeholders. And you need to understand why you're working on something and on what you're working. So let's dive into a few thoughts along that. Of course, we need keys. And let us define first what a key is. A key defines identity. And we leverage keys to express in data what is the same, what is different, and what belongs together. There are 2 main types of keys. On the one hand, it's business keys. They define identity from a business perspective, and they have a meaning to the human business users. So, for example, with our CRM system example from the first chapter, when the business user working with CRM sees a certain customer number, they immediately know, oh, that's a customer number from my client, Rudy. On the other hand, we have surrogate keys, and surrogate keys also identify records, but only technically inside a system. They have no semantic meaning to the user, and they usually also are not exposed to the business users or to the system users. And we use surrogate keys both in transactional systems and in analytics, but for very different reasons. In the transactional systems, they are mostly used to support technical efficiency, to facilitate normalization, throughput, and so on. In the analytics system, we use them mainly to achieve a decoupling from the source systems because we need this decoupling due to our historization. And we also may achieve a stability over time because keys in source systems may change over time and we need to track them in the data warehouse. So we have different sorts of keys in our system and we have different reasons why we use them. And if we mix these different types of keys when we join or when we historize data, this may lead to broken historization and sometimes reports that change results retrospectively. Closely related to keys is table granularity. Granularity defines what a single row represents in a table. So if granularity is misunderstood, our joins may silently multiply data or something else, or numbers explode without warning. And here, for example, in our CRM system example, it's very simple. The granularity of this table is simply customer number. So one row represents a customer. And as in the CRM system, we have no time historization. There is always only one row per customer. When we move on to historize data in the data warehouse, we add the time information. So the granularity of the table changes from only key to key plus time. And there can be certain variations of key plus time, and we will walk through them now, one after another. The first one here is the so-called slowly changing dimension type 2. So we have one version of a row by point in time with each change. And what is very important here, what we also see in this example, is the implicit encoding in the surrogate key. Because look, we have a surrogate key here both in the CRM system, so in the transactional system and in the data warehouse. But while here, the surrogate key has the same grain as a business key. So surrogate key and customer number, it's both grain customer. The surrogate key in the data warehouse that identifies one single row has implicitly the grain customer number plus time. So to work with this table, actually, I have two possibilities. I can work with a surrogate key or with customer number plus time to achieve the same grain. Another form of key plus time is transactions as events and events. We already had them. As we said before, transactions or events happen once, then they are captured and they don't change after that. And for that, we just capture them again with a transaction date. And so here, each single line, the granularity is the event. So each line represents one event, and the event naturally has a timestamp when it happened. What we see here, typically, this is customer account transactions about sales and payments, for example, on my account as client at this company. As opposed to that, another different form of key plus time is a snapshot table. And A snapshot is a record of a certain state at a point in time. Think of it as if you would take a photo. You took your camera, take a photo, you capture the point in time when you took the photo, and then it's fix what you see or what you saw at that point in time. So this example here is a snapshot table that would state the balances of the customer account by month end. And when we look at these two tables, for somebody it may be very tempting to join them by customer number and the date column, because this looks nice. I have a customer number and I have a date column. Perfectly fine. I will join them by that. But as the table have two completely different grains, the result would be nonsense. This is a reason why you always have to think about what is the grain and can I combine these tables, or which logic do I need to apply to combine them? Because of course you can also work with these two tables if you do it the right way. When we have a closer look at the snapshot table, for example, we see that the snapshot per a certain month end is actually the aggregation of the transactions that happened from the beginning of the year until this specified month end by the snapshot. So in practice, very often these snapshot tables are calculated from the transactions, or if we get such a snapshot already from the source system, we can use both tables to reconcile them against each other. Or also we could use in reporting, for example, the snapshot table as a high-level entry point into an overview report and leverage the transactional detail table for a drill-through report into the details. So with that all in mind, let's finish with a few practical habits that I acquired over the years and that I would say help to avoid common mistakes in the daily work. Simple habits make a big difference, and you would be surprised. The first one is, I would say, check your row counts. And it's a fairly simple statement, but checking your row counts also means what I've said before, know your data, because when you check the row count, you have to know what row count am I expecting. And to answer that, I have to think, what is my sources? What grain do my sources have? And what data set do I want to produce? And again, what grain is my target grain? And with that, I can estimate what is my expected result set size. And once having that, after each and every development step I'm doing, I can check the row count and I can check, does it still result in what I'm expecting, or am I missing rows, or maybe am I multiplying rows because of a missing join condition? Sorry. Our next topic is formatting. Those who know me know I'm a huge fan of clean and aligned code formatting. And this is for a reason. Code is read much more often than it's written. And the layout of a SQL statement and its formatting has a very huge impact on how much energy you, respectively your brain, have to invest in reading and understanding the query. Let me give you an example. With this query, try to very briefly and fast grasp which tables are involved, what do you think is the granularity based on the join conditions you see, and what actually is the overall logic that is tried to be achieved with this query. When seeing this and having this question, my brain reacts something like that. On the other hand, the very, very same query, only formatted in a different style, like this, my brain says, oh yeah, this is easy. I can immediately see the tables that are part in the query. I can nicely see the join conditions, how many join condition. I can even visually see if there may be a copy-paste error in the join conditions. And this is really nice. And what is also important for me is when you need not do it this way, but when you stick to a certain nicely formatted, structured style, your brain gets used to it. And after a few weeks or months, for example, you really are able to skip this step where you simply process the syntax and try to figure out, okay, what is a query? And you immediately jump to the part, oh yeah, that's a query. What is a query doing? So you can really focus your energy on understanding the semantics and skip the syntax part. Another one is testing. Testing data sets, I would say, is our everyday business. Very often we have use cases where we do not start greenfield, but we have something where we start to work from. And maybe we have to migrate certain things from one technology to another. We have to refactor something because of performance, or we just have to add some functionality, but make sure that what was there before is right. And I've seen people doing their work and then for developer testing, just pick a random sample of their results and check those in detail. So let's say they pick 10, 15, 20 data rows and check them in very detail that everything is neat and fine. This is fine, but the problem is if you're working with result sets, let's say 100,000 or millions of rows, and you check 10 of them, the odds that you may overlook something is difficult. So I'm saying SQL is easy. Why not check the whole data set and do it with SQL? And this is how I do it. First of all, we have two data sets. In my case, a very small fictive fact table, an old one and a new one with a few rows. And now I want to check, does the new one give exactly the same result as the old one? And we can leverage SQL set operations for that. First of all, hopefully you remember, check the row counts. And when we do that, we already see, oof, the new set has one row missing. So let's dive deeper. And then we leverage the except operator from SQL, because when I have two similar data sets and I'm doing an except, I'm expecting an empty data set. And to do the check the other way around, if I use intersect, I'm expecting everything in the intersect. So let's do except in both directions, old except new and new except old. And to check the opposite, the intersect, and we see, oops, that's not what we expected. But also the second look tells us, oh yeah, that's clear. We have the surrogate key in our comparison, and this is an identity column. This cannot match. So that's easy. We just exclude the columns that we do not want to compare because we know they are different. We're doing that by simply replacing the select all with the list of columns we want to compare. And of course, we don't write them by hands, but leverage a simple query from the information schema and exclude the columns we don't want to have there. And now, executing that again, it looks quite better. We have most of the rows in the intersect, which is really nice, telling us they are completely identical. And we have two rows in the first and one in the second result set, which is telling us we have one row that is differing and another one, remember the row counts, is missing in the new data set. Now, with seeing that, we could immediately jump into the details, do our debugging, and look why these two rows are differing. But sometimes this result may give 10,000, 20,000 differing rows, and then it's also fairly difficult to find the differences. So the next step is it would be nice to have the new and the old row from the differing ones next to each other that I can compare the columns. Let's do that. We just take, again, our except statements and are adding a helper marker, so to say, what is the old and what is the new row. So for the old except new select, we're adding old as marker, and for the new except old, we're adding new. And we're doing a union all over both selects. And then the important step is this result order by the unique key of the row and then our new source marker. And by that, we have the new and the old rows for those that are in both data sets and differing next to each other and can nicely scan the attributes and see, oh, the discount amount is off by a factor of 10. And this is a way I'm using very often in an early stage, and really I could sort out dozens of bugs, I think, throughout my career in an early development stage when doing dev testing. If I hadn't done that, they would have gone to the next environment deployment. They would have popped up in a later stage and caused much more work to be fixed. So apart from that, I would also like to give you some general tips or thoughts. First, with everything that I told before, there is no one shot fits it all. As always, in consulting and in data, it depends. So if something worked in one situation, do not blindly apply it in the next situation. I've seen systems with some sort of this thought that had hundreds of indexes on tables because once an index helped and then we kept on adding indexes for each and every problem. Always take the step back with your knowledge and think, what is the solution to my current problem? Next is learn from others. As you're attending this session and the data community meetings in general, you're already at the right spot, because I believe there is hardly any problem that not anybody else has already suffered from. So reach out, read the overall concepts. There is also a lot of knowledge packed in there, and just leverage the knowledge from others. And when it comes to that, also a thought for know your engine. When you're working with SQL Server and SQL, there will be a point where you have to study reading execution plans, because that's actually the fun thing where you really understand what's happening under the hood. And there is plenty of excellent materials from other speakers out there. Most of it is even free. So I can only highly encourage you to do that if you not have already started. Use AI wisely. Also in the previous session from Benito, we saw a few tips where you can apply AI. And I also made the same experience, what I had to Google for hours 10 years ago. Nowadays is a conversation of 5 minutes with your favorite chatty tool, and you are directed to the correct spot or where you find some solution somewhere. Yet, do not copy paste it blindly. Try to understand what the suggested solution is. Try to vet it with your knowledge and your patterns, and then apply it. And last but not least, keep your architecture clean. So If you define an architecture, if you define your layers, no matter what it is, stick to it. Don't take shortcuts. If you have a problem that needs to be solved in one of your underlying layers, solve it there and not with a quick fix somewhere in the reporting layer just because it saves you 1 or 2 hours of development time. Because this will, over the month and years, this will come back when you have broken the architecture several times and you're ending up not being able to rely on the architecture patterns anymore. So define your layers and stick to them. With that, to wrap it up, what did we talk about? About the concepts, very important, the characteristics of analytical processing, data historization, some modeling and data architectures, that we should work and think in data sets, because in our analytical use cases, set-based always outperforms row-based, and understand your data. Most important, I would say, always ask yourself, what is the grain from what I get and what is the grain I want to produce? If you do that, you will sort out a lot of problems I have suffered in the past years before they even happen. And with that, that's me. That's how you can reach me. I'm happy to get in contact, and I think there is time for a few questions if you have.